Hello, welcome to this lesson. In this video, we are going to learn about a series circuit containing a resistor and an inductor. So I have this simple circuit here where you have an alternating voltage flowing through a resistor and an inductor. Okay, and then the current in this circuit is represented with the letter I. Okay, and then I have this second figure here which shows the phasor diagram for the circuit that we have here. Okay, so let's continue and then look at what you are going to do. Okay, so from this circuit here, we can actually see that the total voltage V will be equal to the sum of the voltage drop across the resistor VR plus the voltage drop across the inductor VL. Okay, this is what you are going to have. But this will be, since you have an alternating voltage source, they are going to be sinusoidal voltage. Okay, so for this reason, you're going to write them in vector form. So you're going to have V to be equal to VR plus VL. Okay, this is what you're going to have. Okay, so now let's come to the phasor diagram that we have here. So from this diagram here, we have the voltage drop across the inductor here. You have the voltage drop across the inductor here. Okay, um, hold on. Okay, so you have the voltage drop across the inductor here, and then you have the current through the circuit to be I, and then this is the voltage drop across the resistor. Okay, and then the V is the total voltage in the circuit, and phi is the phase angle between the voltage and then the current. Okay, so from this figure here, you can see that the voltage drop across the inductor leads the current in the circuit by 90 degrees. Okay, but the voltage drop across the resistor is in phase with the current. Okay, so that's what this figure actually means. And then we've already done this. Okay, I've made videos on this in my previous lesson, so you can check in the description and you see the link to those videos. Please make sure you watch them if you haven't watched those videos. So you know that the voltage drop across an inductor leads the current in the circuit by 90 degrees. Okay, and then the voltage drop across the resistor will be in phase with the current. So that's what this figure actually means. So from this figure here, okay, from this figure here, we can see that V squared equals VR squared, VR squared plus VL squared. Okay, so from here we know that the voltage drop, that's the total voltage in the circuit. Okay, we know that the total voltage in this circuit will be V, and that will be equal to the product of the current in the circuit times the impedance, and also the voltage drop across the resistor will be equal to the current times the resistance, and then that of the voltage drop across the inductor will be equal to the current times the inductive reactance. Okay, so you can substitute all this into this expression that we have here. So when you do that, you're going to have IZ squared equals IR squared plus IXL squared. Okay, this is what you are going to have. But you see that the current is common to all these terms. Okay, so you can cancel the current out. And then when you do that, you're going to have Z squared equals R squared plus XL squared. Okay, this is what you are going to have. So to find the impedance, we just have to make Z the subject by finding the square root of both sides. And when I do that, we are going to have R squared plus XL squared. Okay, so this will give us the formula for the impedance for this circuit. So if you are asked to find the impedance in such a circuit, this is the formula that you are going to use. You may also be asked to find the phase angle between the total voltage and current in this circuit. So from here, from the phasor circuit, sorry, from the phasor diagram, you can see that tan phi, okay, will be equal to the opposite over the adjacent. Okay, in this case, the voltage drop across the inductor will be opposite to the angle, and then the voltage drop across the resistor will be adjacent. So you're going to have VL over VR. Okay, and this will be equal to IXL over IR. Okay, by this current to cancel out this, then we're going to have tan phi to be equal to XL over R. Okay, but I want to find phi, so you will have to take the tan inverse of what you have on the right hand side. So that will give us phi to be equal to the tan inverse of XL over R. Okay, so when you do this, you'll be able to find the phase angle between the voltage and current in this circuit. What you have to know is that the voltage, the total voltage will be leading the current, okay, but it will not be leading it with 90 degrees. Okay, so you have to keep this in mind. So with this understanding, let's try our hands on an example. Okay, so I have this example here which says that a coil has a resistance of 12 ohms and an inductance of 0.1 Henry. It is connected across a 10 volt and 50 Hz supply. Calculate A, the reactance and impedance of the coil, B, the current, and C, the phase difference or angle between current and the applied voltage. So let's look at how you are going to do this. So you have to calculate the reactance in this circuit, and then the only reactance you have in this case will be the inductive reactance. So for that one, that will be XL, and then this will be equal to the product of omega and the inductance. Okay, and then omega, which is the angular frequency, is equal to 2 pi f. Okay, so when you substitute this, I'm going to get XL to be equal to 2 pi FL. Okay, so this will give us the inductive reactance in ohms. Okay, and then from the question, the frequency is 50 Hz. So you're going to have XL to be equal to 2 pi multiplying 50 times the inductance, which is the 0.1. Okay, so let's do this and see what we get for the reactive inductance. We have 2 pi times 50 times 0.1. So this gave me an answer of 31.416. So we have 31.416 ohms. Okay, so this will be the inductive reactance for the inductor. Okay, and then we've been asked to calculate the impedance also. Okay, so let's look at how you're going to calculate this. You know that the impedance, okay, will be equal to the sum of the so the impedance is equal to the square root of the sum of the squares of the resistance and then the inductance. Okay, so you have the impedance Z, okay, to be equal to the square root of the square of the resistance and then the inductance, so plus XL squared. Okay, so when you do this, you're going to have the square root of 12 squared, okay, plus 31.416 squared. Okay, so let's do this and see what you're going to get. We have the square root of 12 squared plus 31.416 squared. So this gave me the value of 33.629. Okay, so let's make it 33.63. So we have 36.63 ohms here. Okay, so this is what you have for the impedance. And then the next question says that we should calculate the current, okay, in this circuit. So you know that for this circuit, you're going to have the voltage to be equal to the current times the impedance, okay? And then we know the voltage to be 100 volts, and then we know the impedance to be equal to 33.630 ohms, okay? So therefore, we're going to have the current to be equal to the voltage over the impedance, which will be equal to the 100 volts over the 33.6 ohms. So let's do this and see what you're going to get. Okay, so this will give us a value of 2.973 2.973 ampere. Okay, so this will be the current flowing through this circuit. And then the last question says that we should find the phase angle between the current and then the voltage. So that will be phi equal to tan inverse, okay, of the inductance over the resistance. Okay, so this will be equal to the tan inverse of XL, which we got 31. We got 31.416. Okay, divided by the resistance, which is the 12 ohms. Okay, so let's do this and see what you are going to get. So we have tan inverse of 31.416 divided by 12. So when you do this, this will give us an angle of 69.09 degrees. So this will be the phase angle between the current and then the applied voltage. Thank you very much for watching this video. Please make sure you like the video and subscribe to the channel.